once again, we'd like to welcome you to Highly Fluorinated Chemicals, a Sticky Issue. And the big picture, I think, is that our planet is filling with chemicals, harmful chemicals, and there's increasing production of these chemicals. The ones we'll be talking about, which are called highly fluorinated chemicals, or PFASs, or sometimes PFCs, it was an old name that was used. There's increasing production. They're extremely persistent, have long-range transport, and there's really only a finite capacity of our Earth to absorb such chemicals. Another problem is that our Toxic Substances Control Act, when it passed, 62,000 chemicals were grandfathered. Even asbestos, which 10,000 people die each year from asbestos disease, cannot be regulated by the EPA. They tried for several years and gave up, so none of those 62,000 chemicals are grandfathered. Of the 23,000 new chemicals since then, 85% have no health data, and 67% have no data at all. With TSCA reform, things should be getting better, but it's a slow process, and there are things that we can do meanwhile. Another problem is regrettable substitutions. On the left, you see a flame retardant called decabromodiphenyl ether, persistent, toxic, bioaccumulative. After years of effort, it was phased out and replaced with decabromodiphenyl ethane, similar concerns. So you spend a long time studying, regulating a chemical only to find the chemical cousin in its place. It's not moving. No. Okay. At our institute, we are scientists who work in the public interest to bring good peer-reviewed science to decision makers to protect health. We publish papers, like on the left. We provide educational meetings, as in the center and this webinar, and we convene. And the folks on the right are part of one of our toxic reductions retreats. At the first retreat, a lot of broad thinkers who really cared about this issue got together and asked, what can we do now, quickly, to reduce exposures to known toxic chemicals? And we came up with 6 classes or families that contain a majority of the toxic chemicals in everyday products. These are highly fluorinated chemicals we'll be talking about today, chlorinated antimicrobials, flame retardants, bisphenols, and phthalates, as well as organic solvents and certain metals. When a chemical is in these families, we ask the question, is this function really necessary? If you say to a mom, you can have a nice stain repellent carpet, but the chemicals that give you that stain repellency may end up in your child's body for years, and they might harm your child's health. That mom might decide that it's not necessary or not worth it to have this stain repellency. And if a function is necessary, then is there a safer alternative to really invest in green chemistry alternatives for chemicals that are in the 6 classes? If you want to learn more, we have 15-minute webinars on the 6 classes. And our exciting news is we have boiled down these 15-minute webinars on each of the classes into a 3-minute webinar with awesome photos and really thought out text. And we're having our online world premiere June 22nd, same time as this, 11 a.m. Pacific. And you should all get invited. We hope that you will join us and share the webinars, the 3-minute video webinars with your colleagues. Okay, I would like now to introduce our first speaker, Mark Strynar, who is a physical scientist at the US EPA, where he develops methods to analyze the movement and fate of PFASs. He's also an awesome woodworker, and I always thank him for the nice wooden cutting boards that he gave us after he spoke at our meeting in February. And I forgot to say that these talks were all presented at one of our meetings in February in person, and so many people missed them and asked if it had been recorded. We thought we would present them again so you could all listen. So Mark, thank you so much for joining us.
All right, thanks for the opportunity, Arlene and Veronica, to talk about this subject. I'm going to jump right into the issue, and because I have a lot to tell you all about that are on the phone and observing the webinar. So next slide, please. So I want to give a little bit of a brief outline, an introduction to per and polyfluorinated compounds for those who are not interested. I'm sorry, for those who are not familiar with what these are, discuss a little bit about the chemical properties and why these are such useful compounds. I want to review a little bit about what's known about human exposure routes, some recent findings from our lab, from a series of recent publications, talk a little bit about human and animal health effects of some of these analytes, and just give some long-term outlook regarding these compounds. Next slide, please. So I think there are two major considerations to think about here when we talk about perfluorinated compounds. Arlene talked about regrettable substitutions, and I think one of those things is about this principle of precaution. When we don't have all the information, when we don't have all the evidence, I don't think that means we shouldn't move on things. And I believe that there are multiple opportunities to sort of see in the past that these compounds have been bad, and some of the things that they've been replaced with are not as good. So with the other one is green chemistry, and we should always strive to go after these least toxic alternatives. And for example, those that turn into something that is harmless, it degrades to its original starting material. And I say the antithesis of green chemistry are polyfluorinated compounds because they tend to have no endpoint. Next slide, please. So a little bit about what these are. These are all synthetic analogs. They're generally long-chain fatty acids, but they are essentially fluorines being replaced on the hydrogens of the compound. They are entirely man-made. There's no natural source for these, and they have immense persistence because of the carbon-fluorine bond. And because of that, they've been detected all over the world in lots of different media. They have persistence, again, because of that inability to be broken down, that carbon-fluorine bond. And because of that, they can bioaccumulate in food chains, including human beings. And that global distribution is also being added to by this environmental persistence, because if it never degrades, whether it moves around in air or water, it can get all around the world. So it's a global issue. Next slide, please. And here are some of the perfluorinated and polyfluorinated substances that some of us know very well, and some of you, I hope, know very well. The two I've underlined there, PFAS and PFAA, are the two most probably widely known and studied. Rob Balot's going to talk in a couple of talks about what went on in West Virginia with the PFAA. But I want you to see that all of these have straight chain, perfluorinated. Every carbon is occupied by a fluorine. They all have lots of different functional groups on the end, and that's what gives them their utility for many uses. Next slide, please. However, what we're beginning to see, it looks like there might have been one skip. No, okay. What we're beginning to see is a switch in a lot of the chemistries. It'll be one more slide. I'll go on after in a minute. They're used in so many different products over the years. Here's an example of some of them. The textile treatments, paper coatings. We have a paper on that recently. Chris knows a whole lot about fire-floating foam, polymers, and carpet. So there's such useful compounds chemically and physically that they're used in many different applications, and that's one of the reasons why we see them everywhere. Next slide, please. Here's one. So what we're beginning to see is the chemistry switching from some of these vendors from the perfluorinated to the polyfluorinated, where some of these carbons are interspersed with ether linkages. Ether linkages making them no longer be just straight chain perfluorinated. Really no data or very little data on the breakdown of these compounds. Do they biodegrade? Do they turn into something less recalcitrant? And the second one down, it says Gen X. We're going to talk a little bit more about that. The other trend is shorter chain compounds. Both ethers and shorter chain is sort of where we're seeing the industry going, with replacement of the longer chain perfluorinated species to sort of get away from recalcitrance and bioaccumulation. Next slide, please. I think you skipped one. Yes. Okay, so what are the documented sources for exposure to humans? Drinking water seems to be the most well documented. We clearly have lots of evidence out there where when these compounds get into drinking water, we see them in the people that are drinking that drinking water. These have fairly long half-life, so we can see them showing up in biomonitoring. In addition, food, and in particular fish and food packaging, these compounds have certainly been seen in. Chris is going to tell you a little bit more next about plant uptake, which is not included on this list of literature. We've done some work to show that house dust is a repository of lots of chemicals, and in particular, perfluorinated compounds show up there very well, and also workplace exposure. So people that are making these things or using these products are certainly those that are getting exposed to these. Next slide, please. So a little bit about these compounds in your water, and this one is shown for PFOA. On the x-axis, what is in the raw water in nanograms per liter, and on the y-axis, what is in the finished tap water. And for the most part, what you see is a 1-to-1 ratio between what's in the raw water to what's in the finished water. And that's because most municipalities do not use something like granular activated carbon or some other means of removing these. What you'll see on the very bottom on the x-axis, there are some of these facilities that were showing very good removal of PFOA because they were using granular activated carbon because they knew there was an issue. And I would say this is similar for a few other polyfluorinated compounds. I would, however, say that as we get to shorter chain perfluorinated carboxylic and sulfonic acids, or even some of the shorter replacement ethers, that this does not hold true. A lot of these are ill-retained. Next slide, please. So here's one paper we published recently. It came from a paper we published in 2015 where we identified this compound we call Gen X here, along with 11 other polyfluorinated compounds we discovered in the Cape Fear River watershed in North Carolina. The municipalities A, B, and C, this is Pittsboro, North Carolina, Fayetteville, North Carolina, down to Wilmington, if you're not familiar with this area. And what we found is that there are both legacy perfluorinated compounds in the water at the A location, and as you move down the stream, there's some dilution of those compounds because there's some point and non-point sources to the north. And then you hit a spot where all of a sudden we see this Gen X compound, and it's fairly easy to figure out there was a fluorochemical manufacturer there that both put this compound into the water as well as about 11 other compounds we discovered. And essentially is a lot of these are unretained by the drinking water process. These locations do not use any kind of advanced techniques to try to remove these. And most of the compounds that we looked at were ill-removed in any of the batch studies we did anyways. And you can read more about that if you want to look at that paper. Next slide, please. A second thing I'd like to point out is that there are novel polyfluorinated compounds being found all the time. One of the things that we do like to do is go and look for the things that nobody has discovered yet. If you're not familiar with this location in Decatur, Alabama, this is a location which was the start of the health advisory, or the provisional health advisory for PFOS and PFOA in drinking water. And it stemmed from the commingling of municipal and domestic waste into biosolids, which were then land applied onto the land in the area. And there was some contamination of the surface water, groundwater, and drinking water in the Tennessee River. And at this location, I've circled that says manufacturing facilities. There's a 3M plant here and a Daikin plant here, both of which manufacture these kinds of compounds. I know for a fact that at this location that we can detect many of the compounds that are affiliated with the production of perfluorobutane sulfonates, or the PFAS minus about 4 carbons, and many of the associated compounds. But what I'd like to show in addition, next slide please, is that we discovered a series of polyfluorinated carboxylic acids. On the top in the A section, this would be the normal way that you can produce perfluorinated chemicals, where every carbon again is occupied by a fluorine. But if your starting materials have every other carbon having fluorines and hydrogens, when you polymerize these together, you can get something such as this. Every other carbon has fluorine, every other carbon has hydrogen. And we imagine that this is probably from the production of PVDF, or polyvinyl diene fluoride. And this is only second behind PTFE, or Teflon as most people know it, in the number of pounds of polymer produced in fluoropolymer manufacture. So this is a fairly high output polymer at this location for sure. Next slide, please. And the last paper I'd like to talk about was this paper we did on fluorinated compounds in U.S. fast food packaging. You can read more about this, ESNT letters. What we found is using this PIGGY method, and PIGGY is called, it's particle-induced gamma ray emission spectroscopy. And this method has the ability to check for fluorine content. And Graham Peasley in his lab did some analyses of paper and paper board, found that there was fluorine signal in many of these paper and paper boards. A subset of these were analyzed by time of flight mass spectrometry. Next slide, please. And what we found is that there are lots of known and unknowns. So when I say known, I mean this was a perfluorinated compound that was known to us, PFOS, PFOA, etc. The unknowns were things that we found to be polyfluorinated. And without going into too much detail, things such as negative mass defect, a homologous series, a repeating subunit, such as a CF2 or a CF2O, we can identify that these are clearly polyfluorinated in nature, but not something that we already know. And those would be the orange bars. So in many of these, there are many things that we do know in the blue and many things we do not know in the orange, but we do know them to be perfluorinated or polyfluorinated. And so there's a lot of additional work that needs to be done to try to figure out what these are, but they were clearly evident in the fast food packaging paper. Next slide, please. If you go to the FDA website and you just do a search for fluoro from the 1,255 compounds for this effective food contact substances, 66 of them have fluoro in the name. Next slide, please. And about 1/3 of those have this structure on the top, which appears to be somewhat of a 6,2 fluorotelomere alcohol acrylate. And so if you look at those structures, anything that comes off of that polymer, anything that comes off of that food contact paper has the ability to be transformed into low molecular weight C6, C5 carboxylic acid with no longer degradation. But there are other fluorinated species that can also be found. Next slide, please. So what's known about the health effects? And this is a very generic health effects slide, courtesy of my colleague Chris Lau here at the EPA. That sort of sets in the context about mouse and humans. On the top, the serum half-life. And what you'll see, for instance, with PFAS, it has an extremely long mouse half-life, 40 days, and a human, it's 4 to 5 years. As you go lower in chain length, you tend to find shorter half-lives, for instance, PFBS, 5 hours in the mouse or 28 days in the human. And as you go longer, they tend to be longer half-lives. I will say, however, that these are not short half-lives. These are shorter half-lives. So if we move away something like PFAS to something shorter like PFBS, acetaminophen has a half-life about 2 to 3 hours in a human. Something like chlorpyrifos is 15 to 30 hours. So these still have fairly long half-lives relative to other things that we either take as a pharma compound on a daily basis, or even some of the xenobiotics we're exposed to as humans every day. There's very little data thus far on Gen X, and that's from the Gannon paper 2016, which appears to be biphasic. It's not really known in the humans what the half-life is, and that's something that needs to be done via biomonitoring. The other thing I want to point out is that a lot of these chemicals have very common or similar effects. This is PPAR alpha activation. And if you just look at PFBA set to 1, every one of these has a common effect, and they're additive, it appears, based on the laboratory data. It's just a ratio of, as you go up in chain length, how potent are these compounds. Next slide, please. So what is known in addition about the toxicity and adverse health effects? What you'll notice here, regardless if it's a mouse or a human, you'll start seeing lots of similarities between those two organisms. For instance, serum cholesterol in the liver and metabolic toxicity, birth weight, growth defects, delayed onset of puberty and the reproductive and developmental toxicity, tumor induction in the mouse and the human and the testes. There is immune effect in both the mouse and the human. There is endocrine disruption in the mouse and the human, and there's neurotoxicity in the mouse and the human, and begins to sort of set the stage. When we see it in the dose rodent model, there's cause for concern potentially for what we see in humans. Next slide, please. So I think there's only 2 slides left. So in summary, most of these compounds that we're talking about do have limited but growing toxicity testing for these. For instance, Adana or Gen X or the 6,2-FTOH, but there's no information on many of the others, some of the compounds we've discovered or others. This toxicology has been found to be more favorable, and I quote that from a brochure from DuPont on Gen X, but not non-toxic based on the studies by Ray, Gordon, and Serex. The shorter chain PFASs are almost completely adsorbed because they're shorter chain, they're orally taken up very easily, they're more rapidly eliminated, but they're poorly attenuated in traditional drinking water systems, and we can see that from our pubs and other people's pubs. In general, the environmental bioconcentration is of shorter concern for the chain lengths that are short, but they have been shown to occur in fish in one particular example for this FBSA. I will point out that the terminal per and polyfluorinated metabolites, however, do remain recalcitrant, meaning they do not degrade further in many instances. Next slide, please. So, future perspectives. There is definitely still going to be a demand for these compounds. They're absolutely very useful for many different applications, and we're seeing this switch to some of these developing countries, in particular China. I've been reading a lot of papers on. The next generation of these replacement compounds being produced are still unknown in many instances for their identity, and the health effects are certainly relatively unknown. The environmental and health effects research on these replacement compounds is ongoing. Preliminary results appears to suggest they're similar to the compounds they're replacing. So getting back to this regrettable substitutions Arlene talked about, there is new research on human exposure to PFASs and their adverse health effects and their ecological impacts, and we will need to do this to support risk assessment and reg decisions. And we do know that virtually every person has these compounds in their body, their blood, potentially their urine, and we'll need to do additional biomonitoring studies to figure out where things are going in the future regarding these compounds for legacy and replacements. I believe that's my last slide.
Okay, thank you so much, Mark. That was great. And these slides will be available if anybody wants to go back and check out the references. I'd now like to introduce Dr. Christopher Higgins, who's an associate professor at the Colorado School of Mines, and his research focuses on safe transport and bioaccumulation of perfluorochemicals and other emerging contaminants in aquatic and terrestrial systems. And he particularly has done very interesting work on the uptake of perfluorochemicals into food crops.
I really appreciate the opportunity to talk, Arlene and Veronica, with this audience on the work we have done on the accumulation of these perfluoroalkyl acids in food crops. Next slide. So Mark did a very great job overviewing the types of products these chemicals are used in, as well as the types of chemistries. Today, I'm going to focus on one particular route that these chemicals can get into our food crops, and that's the fact that when these products that we have in our house or we use with our food packaging, that sort of thing, are used, often some of these chemicals can get washed down into our wastewater treatment plants. And for those of you who are familiar with wastewater treatment plants, there are basically two things coming out of the plant typically. There's the effluent that gets discharged to the local river or the ocean, depending on where you are. But there's also a solids content that comes out, the sludge, also referred to as biosolids if it's appropriately treated. And both the biosolids and the wastewater effluent or reclaimed water can be used in agricultural settings. And so biosolids can, with appropriate controls, be used in agricultural fields and even sold for use in home gardens if there pathogens have been treated, for example. And in some states, particularly California, Texas, and Florida, which have had some severe water stresses in the last couple of years, effluent is somewhat commonly used to irrigate some food crops. And why this is relevant is that when the fluorochemicals are released to the wastewater treatment plant, depending on their properties, the shorter chain length or longer chain length chemicals, they can be released both to the biosolids as well as in the effluent. And that is a potential route for these chemicals to make their way from essentially consumer products into your lettuce or tomatoes or strawberries. So next slide. So what I wanted to point out here, and this hints a little bit at what Mark was referring to before, is it's not just the perfluoroalkyl acids that we need to be thinking about, even though that's what I'm going to be talking about today in terms of their accumulation. These chemicals down here at the bottom of the screen, PFAS and PFOA being two representative ones, are essentially terminal end products. But these chemicals can also arise from polyfluorinated compounds or precursors, we often refer to them as. And these chemicals tend to accumulate in phases such as sludge and in the biosolids. And so when you're released the environment. Next slide. So this is a slide from an earlier paper that we looked at, essentially the amount of these chemicals in a typical biosolids-amended soil. And why this is important is it really speaks to the persistence of these chemicals and the fact that it really only matters the total amount of biosolids that were applied at a location to make a prediction as to what the concentration of fluorochemicals might be in that soil. Of course, it does matter somewhat what the concentrations were in the original biosolids, but if you apply 600 tons per acre of biosolids over the years, you could expect a certain concentration of PFOA or PFNA, which is slightly longer chemical, or PFAS in that soil. So it really is a cumulative use of these chemicals and cumulative loading of biosolids into soils, which can result in elevated levels in these biosolids-amended soils. So, it's a very clear relationship in terms of these chemicals being released in biosolids and that being applied to soil and the levels that accumulate in the soil because they really don't degrade. Next slide. So you might ask, why would we be concerned about uptake into crops? And to illustrate the importance of that, I'm going to refer back to some work that was done a number of years ago out of University of Utah. Bill Doucette really kind of challenged the traditional model of plant uptake, of organic chemicals, I should say. And to think about this, we need to think about this transpiration stream concentration factor, or TSCF, which is really basically the concentration of the chemical in the xylem or the blood of the plant, if you will, versus what the plant is being exposed to in its roots or in the solution adjacent to the roots. And the traditional model had been that only chemicals that had this somewhat magical log KOW value of about 2, and if you don't know what log KOW is, it's simply a way of predicting how hydrophobic or lipophilic a chemical is. So the idea is that these chemicals only have log KOW of about 2 would accumulate, but Bill Doucette's lab really kind of turned that on its head and said, it's really the water-soluble compounds that would have a very high transpiration stream concentration factor. And so the plot on the right is from the kind of more updated model looking at accumulation of chemicals in crops. And the reason that this is important for fluorochemicals and other emerging contaminants is that many of the chemicals we're interested in are very water-soluble. And if you were able to measure a log KOW value, which you really can't for these compounds, they would tend to be on the left side of that right plot. So we would expect them to have relatively high transpiration stream concentration factors. And so that was really the motivation for us looking at this issue. So next slide. So I'm going to focus today on the biosolid studies. I just will mention that we did also do some work with reclaimed water and accumulation from reclaimed water of these chemicals being in reclaimed water. And I'm also going to primarily focus on the greenhouse studies, even though we did do some pilot scale and field-based studies. I'm really going to focus on the greenhouse simply because of the ease of interpretation of some of those results. But I'd be happy to answer questions later about some of the other studies we did. Next slide. As Mark alluded to, it is not super easy measuring these compounds, although he made it sound so. So you do have to have very robust methods to measure these compounds in whether soils or sludge or plants. And all the data I'm going to present is we've measured these chemicals via liquid chromatography, tandem mass spectrometry, with appropriate controls to ensure we're getting accurate results. So the next slide. So in terms of the experiments, again, focusing on the biosolids, we looked at a variety of crops. And the idea here was to look at different types of crops where you would be eating a different portion of the plant. So if you're going to eat a root crop, such as carrots or radish was the crop we chose, there might be crops where you would eat the stem or leaf, such as celery. Lettuce is pretty easy. You're eating the leaf of the lettuce plant. And then we also wanted to look at fruit or fruit and seed type crops. And so the fruit crop we chose was tomato, and the fruit seed was a sugar snap pea. These were all crops that were relatively easy to grow in a greenhouse environment. We did look at 3 different soils. One was a control soil, one was a field collected biosolids-amended soil, so a typical municipal biosolids-amended soil. We also created one soil in the lab, mixing the control soil with composted biosolids from an industrially impacted wastewater treatment plant. So this is going to have elevated levels of these compounds because of the fluorochemical industry in the sewer shed for that particular plant. So we exposed all these different plants in these different soils and essentially looked to measure these chemicals in the plants. Next slide. So focusing first on the lettuce and tomato, just on the edible portions, it wasn't too hard to see these chemicals in the lettuce leaf and in the tomato fruit for the different types of soils we were looking at. So what you can see here is the industrially impacted soil. We tended to have higher concentrations in the lettuce. We tend to see lower levels in the tomato fruit, and we'll get to explain that more in a moment. But what's really important here is not so much looking at the actual concentrations, but thinking about the concentration of the chemical in, say, the lettuce leaf versus what was in the soil. And so the next slide is a way of, provides us with a metric to look at that. And so the bioaccumulation factor, or BAF, it was a rough metric used to look at the concentration of a chemical in the plant, various plant tissues, so leaf or fruit, versus the chemical in the media. And so in that case, it would be the soil, or it could be in the water. Now, this is a useful metric because it's, we can compare different chemicals, but we can also use a BAF for risk assessment purposes down the road. So next slide. So this takes that same data I presented earlier and translate those concentrations into BAF values by comparing them to the concentration in the soil. And this is where it gets very clear that when you look at the log, the base 10 logarithm of the bioaccumulation factor, which is the y-axis here, versus the carbon tail length, so these are just the perfluorocarboxylates shown here, there's a very clear relationship, at least for lettuce, in the various soils, where we see higher accumulation of the shorter chain length perfluorochemicals in the lettuce. And so this is basically relating, again, the lettuce concentration in the leaf as compared to the soil. And it's a very clear relationship. Even though the concentrations are all different between the chemicals, we see higher accumulation of the short chain compounds in the lettuce leaf. The tomatoes are a little bit different, but I'll touch more on that in a moment. So the next slide. This shows you that when you're looking at the different compartments of the plant, you also start to see these differences. So on the left, we see the celery root and celery shoot, separating those two. And on the right, we have pea, fruit, shoot, and fruit. And you can even see here where we've plotted the concentrations of the short chain carboxylates on the left and the sulfonates on the right. And for both of these two figures, you tend to see higher concentrations of the shorter chain compounds in the shoots, and the longer chain length compounds tend to accumulate more in the roots. And in the peas, the highest concentration of was for the perfluorobutanoic acid, for example. And the next slide illustrates that further. So this is the log of the fruit soil concentration factor versus carbon chain length, and it shows a very good relationship between the concentration in the fruit and the concentration in the soil on a log scale. And what this shows is the tomato and peas kind of behave the same way. And we see about, for every 2 carbons we change in terms of perfluoro chain length, we see about a 10-fold increase in the concentration in the fruit. So what that means is that if you had a soil that contained equal concentrations of PFOA and PFHXA, so the C8 and the C6 versions, if the concentrations in the soil were the same and you grew your tomatoes in them, you would have about 10 times as much of the hexanoic acid in the tomato fruit as you would the perfluorooctanoic acid. So the next slide really tries to sum up all of this. And what we are trying to say here is that we definitely see accumulation of these perfluoroalkyl acids into plants from either biosolids-amended soils or reclaimed water, a data I didn't quite show. We tend to see shorter chain length compounds being more accumulative than longer chain length compounds. The carboxylates also tend to be more accumulative than the sulfonates. Again, I didn't get into that level of detail. We tend to see the short chain compounds more so in the fruits and the longer chain length compounds in the roots and shoots. All the data we have suggests this is very much a passive uptake process for the chemicals in terms of their movement from the soil or water into the plant. And what this really does is it suggests this new plant accumulation model is somewhat consistent with the newer models, but keep in mind that the newer models also suggest that charged compounds would not be accumulated. And all these compounds I looked at here are negatively charged at environmental pH values. And it really does point to the need that since these compounds are just as persistent as the longer chain length compounds, they will more readily move their way into plants, and that could be a longer term issue with respect to exposure to these chemicals. So my last slide is just a disclaimer. Some of this work was funded by EPA, some of it was funded from the US Department of Agriculture, and some of it was associated with an NSF Engineering Research Center that I am involved in. With that, I'll put the baton back.
Thanks so much, Chris. That was great. I first really learned about this reading a book that was published in 2007, way back then, on the hidden dangers of C8. And after that, got together with a group of scientists. We started having monthly scientist calls. Right now, there's 75 scientists from all over the world joining our calls. Some of those scientists put together the science in a statement called the Helsinger Statement, published in 2014. But still, national media was really not covering these chemicals. And then in 2015, we published the Madrid Statement, where 230 scientists from 40 countries called on the international community to cooperate in limiting the production and use of, can you hear me? Yeah. Limiting the production and use of these chemicals and developing safer alternatives. This was published in Environmental Health Perspectives, and with a lot of media, and things started to change. And later, Sharon Lerner did a great news series called The Teflon Toxin that we'll recommend. And then, of course, the article in the New York Times Magazine about Rob's work, which really contributed to everything changing. At the same time, in November of 2015, California Biomonitoring, and that's a group that we have legislation to biomonitor people in this state for chemicals of concern. And they were able to put the whole class of highly fluorinated chemicals, all 3,000 of them, as priority chemicals for biomonitoring, which means that the whole class, all 3,000, are on an authoritative list. After Rob's New York Times magazine came out, the governor of New York has Hoosick Falls and a number of communities with quite high levels. There had been a provisional health advisory in January 2009 of 400 parts per trillion for PFAA and 200 parts per trillion for PFAS. And the governor and others, the health department from New York, wrote to the EPA asking them to please set a lifetime level. And in May 2016, a lifetime level of 70 parts per trillion was set. That's about a tenth as high as the provisional level. Meanwhile, we had been doing a study looking at communities. The EPA had been measuring a number of PFASs in drinking water and found relatively high levels. We did a study, the first author was Cindy Hu at Harvard, going from the drinking water with high levels back to point sources, and determined that a lot of the polluted water apparently was linked to industrial sites, military training sites, airports, and wastewater treatment plants. And she determined 6 million Americans had levels above the EPA level. This led to great concern with the military and airports, and the Air Force stopped using all foam-containing highly fluorinated chemicals in their training exercises, which is a really good thing. We're hoping the rest of the military will follow suit. But unfortunately, down at the last slide, slide 55, it says they will replace C8 foam with C6. And that means instead of C8, which is fairly easily filtered out of drinking water by activated charcoal, they would be using C6, which is much harder to filter. And firefighting foam is a number of complex molecules, not just one, lots of different kinds of C6 and other molecules. So we don't have time now, but just to say, if you want to learn more about fluorinated alternatives, on our website, you can download a sheet on highly fluorinated chemicals, and the fact that as we're learning, the short chains have some fairly undesirable qualities, perhaps even more undesirable than the long chains, is that they cannot be filtered out of drinking water, and they do tend to accumulate in food crops. And they do not stay in human serum as long as the long chains, but a couple of recent studies show that they seem to accumulate in organs like brain and liver and kidney, and indeed some of the same organs that have been found to have cancer from exposure to the C8. So it is a real worry. And the short chains, in many cases, accumulate in human organs at a higher level than the long chains. An interesting story from Denmark. The Danish co-op, half the people in Denmark belong, about 2 million, decided not to sell any products with any highly fluorinated chemicals. And they discovered they couldn't sell microwave popcorn anymore. And there were headlines in Denmark, no more microwave popcorn at co-op. And then an entrepreneur in Czechoslovakia came up with an alternative for microwave popcorn bags that did not require any PFASs. So we think that by phasing out the whole class of these chemicals where they're not really necessary, that can lead to innovation and alternative products that have the same function. Interestingly, now there's some legislation here in California. There's Bill 958 that says food or fast food packaging should not contain any PFASs. Vermont has a pending bill that also would prohibit all PFASs, and Washington State is proposing to add the entire class to the list of chemicals of high concern at an upcoming hearing. I had an editorial in Science with the good news that companies are phasing out the whole class of highly fluorinated chemicals and other chemical classes. I mean, we believe that this is necessary to avoid regrettable substitutions, to encourage green chemistry and really make a difference. And under the photo, you see the question, do we need this chemical given the potential for harm? And I think when a chemical is in the 6 classes, this is the question we want to ask. So all these brands are eliminating, they're in the process of eliminating all highly fluorinated chemicals from the products they produce and sell. The idea of taking out PFASs, we worked with IKEA, who attends our workshops, and IKEA said that they thought they could remove them. 9 months later, they did remove all their PFASs. They said from most of the products they sold, except a few fry pans. At another meeting, they came back and announced that, and several companies at the meeting, such as Kaiser Permanente, said if IKEA can remove highly fluorinated chemicals, so can we. And so Kaiser is phasing out all PFASs and all flame retardants from furnishings and other purchases. So an email I got that made me feel pretty happy from a large retailer who I won't mention their name right now. They said in another couple of weeks, we'll stop offering C6 chemistry fabric protection as an optional add-on. Tonight, I will open a nice bottle of Merlot and share a toast with my wife over the fact that we've made a few more products safer for a few more people in this world. So the good news on our side is if retailers, manufacturers, purchasers, people who are making decisions about products understand that this whole class of chemicals is extremely persistent. There are no known breakdown pathways. I've heard people say they last for geologic times, millions of years. The whole class does. And the potential for harm, that we really don't have enough information to know that these new substitutes are safe. They can voluntarily say, let's look for healthier substitutes. So remember, is it necessary? Is it worth it? Is there a safer alternative? So once again, I want to say we're having our online premiere of the 3-minute videos. It'll be an hour-long conversation with some leading scientists and other thinkers talking about toxic chemicals, watching the videos together. The first will be June 22nd, and there'll be 3 of these hour-long discussions looking at the videos and learning more. So we hope you'll join us. You'll be getting an invitation soon. Quickly, we're hiring. If you're interested in working with us, go to our website. And I want to thank our awesome speakers. There are their emails. They're all willing to answer your questions directly. We have some interesting reads with links, and you will get these. You already should have all received PDFs with these. I really want to thank Veronica and Rachel and Tom of the Green Science Policy Institute for their excellent work making this possible.